Hi everyone, welcome back to SAT 2 Math 2C. So we're going to continue on our topic today, discussion of polynomial. Remember, we started our whole discussion with polynomials. We went through the fundamentals polynomials, we went to the first degree polynomial, second degree polynomial, which would happen to be quadratic, which you guys are very familiar with. So we're going to step up a little bit. We're going to talk about polynomials that are more than 2 degrees, which is a little bit difficult. Because keep in mind, what is the goal of solving polynomials? The goal is always to what? Find 0, right? We want to find out what are the zeros of a polynomial. For the second degree polynomial, for instance, if I have p of x is equal to ax squared plus bx plus c, right? At second degree, I have different ways of solving this. I can factor. I can try different manipulation of the equation. But at the end of the day, there's always what? A quadratic formula that allows me to solve this. That simply says the root, or the 0, as you guys probably know this. You can always use the quadratic formula, right? Which is negative b plus minus square root of b squared minus 4ac divided by 2a. Right? Doesn't matter. I mean, you might be able to factor, you might not be able to factor, but it doesn't matter because you can always find a root that way. So it's a guaranteed way, right? So what if, so this is what we talked about in the previous topic. So what if your function gets a degree higher? What happened to the third degree? Is there a such thing like a panacea, like the formula that allows you to solve the entire solution? No, unfortunately there isn't. Okay? But there are different theorems that we can use that will allow us to find the roots. And just overall, sort of a big picture thing, the goal is try to reduce everything down to a second degree polynomial. Okay? Why is that? Because once you get down to the second degree polynomial, guess what you have? You can always use a quadratic formula to solve for roots. Okay, so keep that in mind. Doesn't matter if you have a third degree, a fifth degree, a 20th degree polynomial. The goal is try to reduce that polynomial all the way down to the second, because when you get to that, you can use the quadratic formula to actually find the roots, right? So let's kind of do some house cleaning topic before we go on discussing how we can different roots theories we can have. Right? Let's talk about division. Kind of important. How do I do division, in this case, of polynomials, or p of x, right? The way you do this is actually the same way you do all divisions. Let's say I want to divide 5x squared, now let's make a cube, plus 2x squared minus 3x plus 10, right? I want to divide this by x minus 2, right? So keep that in mind. We're going to use this example throughout. So what do? Well, we literally do this like a regular division. That's the traditional approach. Let's show you how to do that. You set up your division like this. 5x cubed, right, plus 2x squared minus 3x plus 10. And then here you have x minus 2, right? That's how your usual division works. You try to come up with a term that will match the first term, right? So what do you have to multiply x by to get 5x cubed? Well, 5x squared, right? Because if you do 5x squared multiplied by this, you get 5x cubed, which is great, right? But don't forget you got this guy, so you have minus 10x squared, right? Not bad. What you do is you end up subtracting this, right? So this becomes 0. That's why we did this whole exercise, so we can reduce it down to the next term, right? And so what's 2x squared minus 10x squared? That's 12x squared minus 3x, right? And you repeat the same exercise. What are you going to get here? 12x. What would I have to multiply this guy by to get 12x squared? It's simply what? 12x. So you get 12x squared minus 24x. Again, keep in mind you're subtracting. I mean, you don't have to really do the subtraction, but when you're initially doing this, just, for your own sake, try to do that. So it's minus 3x minus plus 24x, so it's 21x plus 10, and you know the answer, right? Do the same drill again. You have to add 21, because that will make it 21x minus 42, right? And if you do the subtraction again, you're going to end up with 52, right? Assuming my math is right. So this is not bad. This is a little bit tedious. It's not bad, right? You just got to keep track of things. But so the way you would put this is equal to 5x squared plus 12x plus 21 with the remainder of 52. Okay? Remainder of 52. I'm pretty sure you're going to have plenty of practice that you're going to have. So practice this, okay? Make sure you know how to do this instead. I'm just showing you an example, show the mechanism how to do this. Not bad, right? Not ideal, not fast. But why are we doing division? Why am I also interested in division? Look what I did. What is this polynomial? It's a third degree polynomial, right? When I divide it by a first degree polynomial, guess what I get? I end up getting what? A second degree. Remember, the theme is what? Our goal is try to reduce a polynomial down to the second degree, right? And the way to do that is through what? In a sense, factor in a division, right? If we can take out something, and then we can do the division, it will reduce the remaining portion of the polynomial a degree less. And imagine you keep on repeating that exercise, you'll be able to get down to the second degree. Now, of course, this is a little bit far because you said, well, this is kind of a random game. We're going to show you how to do this properly. Okay? So this is the division of polynomial and how do you do it traditionally. Okay? You said, well, this is not exactly the best way to do this. Tedious, right? I completely agree. That's why we have the next approach. I'm going to leave this on the board because I'm going to show you that we are going to be able to get the same results all over again. So the second part is really how do we use synthetic division. Okay, how do we use synthetic division? Synthetic division only works if you're dividing a px divided by x minus c, c being a constant. Okay? It only works when it's dividing x minus c. Well, what do you say? What if I have x plus 2? Does that work? It works. In this case, what's c? If you were dividing x plus 2, your c is going to be what? Negative 2, right? Because it's x minus negative 2. So keep that in mind. So it's not just subtraction that we work on both, right? The way you set up synthetic division, okay, is that you put all the coefficients. You only need the coefficients. And in order of the highest to lowest degree. So you have 5, 2, negative 3, and 10 in this order, right? Third degree, second degree, first degree, 0 degree. In case you're missing one, let's say this term isn't there, guess what? You have to put a 0 there instead, okay? You cannot skip a term. And then here, you put c, okay? In this case, what's my c? It's 2, right? I'm going to show you how easy and how quick this is. All you have to do for synthetic division is carry down the first number. I actually do an arrow just because it reminds me, right? And what you do is you multiply and put that number there. What's 2 multiplied by 5? 10, right? Then you add here. What's 2 plus 10? 12, right? You repeat the same thing again. 2 times 12? 24. 24 plus negative 3? 21. Right? Pretty fast. 2 times 21? That's the one I was struggling with, 42, right? And you get 52. You say, well, this is a stream number that doesn't make any sense. That's not true. Your last term is your remainder, and this is your quotient. So you have 0. You remember, it's getting reduced one term, right? So it was a 3, 2, 1, 0. Now it's going to be what? 2, 1, 0. So it's 5x squared plus 12x plus 21 with a remainder of 52. Ha! Does that match what we did before? Exactly, right? So it's a really, really quick way. All you have to do is what? List out the coefficients, and you're done, right? Let me show you in case a number is missing. Let's try this. 5x to the 5th plus 2x plus 1 divided by x plus 1. You say, all right, Len, this is pretty messy. Can we do synthetic division? Now, absolutely. We list out the coefficient 5, 0 to the 4th, 0 to the 3rd, 0 to the 2nd, right? We don't skip terms. 5x to the 5th, 4th, 3rd, 2nd, and then there's a 2, and there's a 1. And what'd you put there? Well, it's minus c. In that case, c is what? Negative 1. So it's negative 1, and then you do the same thing. Carry down a 5. Okay? That 1, negative 1 times 5? Well, negative 5, right? Add negative 5, multiply 5, add 5, multiply negative 5, add negative 5. Multiply 5, add 7. And then multiply negative 7, negative 6. Last term is your remainder. The rest is your, so start of the 5th term, so this is what? 5x to the 4th minus 5x third plus 5x squared minus 5x plus 7 with a remainder of 6. Bingo, you're done. Okay? So this is a really quick way, right? With synthetic division, you almost never ever had to do regular division. Right? It's just a lot faster. However, would I be able to do this? The answer is no. You cannot do that because the rule of synthetic division is you can only do a polynomial divided by a linear polynomial. Okay? I'm not worried about that because I'm never going to actually do this when I try to find zeros. Okay? So that's pretty cool, right? Let's keep that in mind. So we really just went through a really, really cool and easy way to do division, and that is guaranteed on your test, right? Okay, so if they ask you to do division, really quick way to do it. You save time, you save energy, you increase accuracy. Okay? Now, let's take a look at so the question is, how on earth, this is beautiful, but how on earth am I going to know what c I need to divide by? Right? Let's kind of look into that a little bit. Let's look at the remainder theorem. The remainder theorem says if you have a polynomial p of x divided by x minus c, you do not actually need to do the entire division to get the remainder is. You say, that's crazy. What do you mean? Your remainder is actually p of c. Okay? Your remainder is actually p of c. You say, whoa, hold on. That can't be true. It is true. Let's try this, right? This is my polynomial, 5x cubed plus 2x squared minus 3x plus 10, divided by x minus 2, right? What's my c? c in this case is 2, right? Let's pop it in. What's p of 2 in this case? It's 5 times 2 cubed plus 2 times, right? Instead of x, I just put 2 there. 2 squared minus 3 times 2 plus 10, right? Do the math. What is this? 8, 5 times 8, 40 plus 8 minus 6 plus 10. What are we going to get? 48, 42. We're going to 52. Okay? That's it. Really, really quick way. Remainder theorem is important because it says you do not actually have to do division to get your remainder. All you have to do, just pop this in. Okay? You pop in a c in a polynomial, you get your remainder. That's it. Right? That's it. And you say, well, that's cool, but it's kind of useless. I mean, it's a cool thing to know, but how does that help me? this is the next part is what really helps you. What happens if your remainder is 0? What do we call that? Right? What happens when you do 26 divided by 2? You get 13 and the remainder is 0. What do we call 2 or the 13? These two are the factors, right? If you're divided by a number, you get a quotient out of it, and the remainder is 0. Both numbers are factors, and then you have what? And you can say 26 could be written as 2 times 13. I mean, this is a really silly example, right? But that's what it is. You can write it as that. Do you see where I'm going with this? If the remainder is 0, then whatever you divide it by has to be a factor, right? Let's take it one step further. If what you divide it by is a factor, then you can take it out, and you have a 1 degree less of a polynomial. Think about it. If you have, you see where I'm going with this factor theorem, right? Factor theorem simply says if you do this, if the remainder, which is P of C, is equal to 0, then x minus c is a factor of P of x. Okay? Right? If the remainder is 0, then this guy that I'm divided by has to be a factor. And what's the benefit of having a factor there? Then I can write P of x is equal to x minus c times a degree that's less. That's how I reduce the polynomial. Okay? That's how I reduce the polynomial. It goes a degree less. Think about it. Let this process in your head and realize this is a really powerful statement, right? All I had to do is pop that number in and see if it's equal to 0. If it is, I'm done. Right? If it is, I am done. Okay? And once I find out it's a factor, then it will be reduced to a lower term, right? If I find out that I can have another factor, x minus c2, right? Let's call it c1. Then this guy will be xn minus 2 plus it will be reduced 2 degrees lower. And you go on and on. If it's 20, you do this 18 times. You have 18 factors and a polynomial, and you get your roots, right? Because what's the root of this? The root is what? c1. That's easy, right? We don't need to do any math with that. Okay? So this is where we're going. So if the remainder, the factor theorem says, if the remainder is 0, okay, then x minus c is a factor of P of x. I'm going to continue to add a line to that. Then you can write P of x as x minus c times x to the m minus 1 plus all the way down. You're reducing that a degree lower. Okay? Now, here's my question. Is x minus 2 a factor for this guy? No. Why not? Because you get a remainder, which is what? 52, right? So x minus 2 is not a factor. Okay? So, how does this work? Let's take a look at an example, right? For instance, I have, well, obviously, I said it, right? This thing doesn't work. If I have my polynomial is x to the 5th plus 32, right? And I have x plus 2, is that a factor of this? Okay, that's the question I'm asking. Is that a factor of this? All we had to do is what? Pop into the remainder theorem, see if it's what? If it's 0, that's all. What is the c in this case? C is not 2. C is what? C is negative 2. Right? C is negative 2. And so when you pop it in, P of negative 2 is negative 2 to the 5th plus 32, which is negative 32 plus 32, which is equal to 0. So if P of C is equal to 0, then what? This is a factor of this. Okay? That's been confirmed, and what you can do is what? Reduce this. Okay? How do we reduce this? We can reduce this by synthetic division. Right? See how everything comes together? We want to write this as x plus 2 times x to the 4th something else, right? But how do we know what that is? We just simply do the division, right? Because if it's a factor, I just need to divide by that to get the remaining division, right? So what we're going to get is, let's say, 1, 0, 0, 0, right? Because 5th, 4th, 3rd, 2nd, and 1st, and 32, right? 5, 4, 3, 2, 1, 0. Right? Make sure you don't skip the 0 because there's nothing in between. Be careful. My factor is negative 2, right? C is negative 2. So all I have to do is just do my synthetic division, and all should be good. Carry 1 down, right? Negative 2, add negative 2, 4, add 4, negative 8, right? Negative 8, add 16, 16, negative 32, 0, there, see? That's why it's a factor, because the remainder is 0. So all this is what? X to the 4th plus, or minus 2x cubed plus 4x squared minus ax plus 16, right? So let's write this out. So it's x to the 4th minus 2x to the 3rd plus 4x squared minus ax plus 16. You just reduced a 5th degree polynomial down to a 4th degree polynomial. And we already got one of the roots. The first root is what? Negative 2, right? And you continue to do that and see what factor this is that will go into that, right? And you'll be able to get the answer. Okay, we do one more time to get x to the 3rd, right? You do one more time to get x second, and then afterwards all you have to do is, you know, quadratic formula, right? That's all you have to do. Okay? See where this is going? So keep on practicing. Just pop in, and then pop in, find an x of c, and then pop in and see which one works. Okay? So we're getting there, right? We're getting there. So Lynn, this is great. You know, you guys learn how to kind of like move down a level, move down a level, move down a level. Here's the question: how do I know what c is? You got lucky here because you're probably looking at the book and say, oh, well, this works out, so that's why I put it on a board. How do I know what c is in this case? Right? I didn't leave you hanging there. All it is what? That's what part 5 is about. Part 5, or really the last part of today's topic, the rational root theorem. The rational root theorem says, if you have a polynomial right? If you have a polynomial, you have, let's say, let's write it this way. an xm plus am minus 1 xm minus 1 plus all the way a1 x1 plus a0, right? This is your generic polynomial. Rational root theorem says if you have a rational root, which means what? Well, rational, not imaginary, like, right? If you're that can be written as a fraction, right? Let's review that. Rational means could be written as a fraction. In other words, it's not a never-ending, like pi. Pi is not a rational number because it's never-ending. It cannot be written as a fraction. Rational root theorem says if you have a rational root, right? Something that can be written as a fraction, that root has to be in the form of p divided by q, where p is a factor of a0 and q is a factor of an. All your roots are included in this case. Let's take a look at the previous example. We have what? We have p of x is equal to x to the 5th plus 32, right? The way I always do this, I will write all possible roots will be all the factors a naught, which is the constant term, right? What are factors of 32? Well, let's plus 1 plus minus 32 plus minus 2, and what's 2? 16, right? Keeps on going, plus minus 4. Always do them in pair, plus minus 8, right? Anything else? Yeah, that's it, right? So all these could be what? The enumerators. And the denominator is easy. It's just plus minus 1, right? Because it's 1 in front of it. In other words, this has to be what? A combination of all these. You say, well, that's a lot. That's not really, because it's plus minus 1. Basically cancel out a plus minus sign. So all the possible roots, I'm not saying they are the roots, but if it's going to have one, they're going to be on this list. Plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16, plus minus 32. Okay? This is a list of all possible rational roots that's going to work for this guy. If it's not there, it's not there. Okay? So you are not guessing. You're not guessing this x minus c. You're not guessing the c out of nowhere. There is a rational. Okay? Right? There's a rational way of getting this is what you look at. Right? In other words, you can just write this as c. That's what it is. Right? The rational root. It's here. Right? So what you do is literally you come up with this list and you pop it in. Use the factor theorems to if it works. I'm going to pop in 1. That obviously doesn't work. -1 doesn't work. Right? What else? Let's pop in 2. 2 doesn't work. Too big. I can pretty much conclude that anything at this point, and the positive is just too big. It doesn't work out. Negative, on the other hand, works. Right? If I pop in -2, that works, because if I pop in -2, I get -32 plus 32. I get 0 out of it. So I know -2 is an answer. Okay? I know -2 is an answer. And once you know that, you're set. You reduce it down. Okay? You reduce down. So this gives you a list of all possible rational roots. Next question. What if I can't find it here? How many roots am I potentially supposed to have here? 5. That's the maximum number of roots. Why? Because that's to the 5th power. I found 1. What happened to the other 4? Well, I don't know what happened to them, but they are not rational. Okay? They're not rational. So what does that leave us? They are either irrational or they are imaginary. AKA they don't exist in the real world, but they are imaginary. Okay? And we're going to talk about this in detail in the next lecture. How do we deal if they happen to be imaginary? Okay? But with these five rules or 5 little steps, you can actually find out how to get all the rational roots out of them, as many as you can.